Hello, my name is John.Riley with Samtec. I'm a senior technical marketing engineer, and today we're going to talk about optimized component thermal management and mitigation techniques in high-performance computing applications. Or, let me say it a different way for you. Today we're going to talk about high-performance computing applications while we optimize the components for thermal management, or hot stuff. And I am the senior technical marketing for the user experience and developing thermal solutions, or Samtec's local stud. Now let's get on with the presentation. Samtec is a producer of interconnects all ranges of product types, from power connectors that we'll talk about that will use different techniques in thermal management to high speed and high performance cable solutions. Each of these will have different options for thermal mitigation and thermal optimization. In this presentation, we'll talk about three different types. We'll talk about air cooling, localized, and immersion cooling, and how we optimize these components for signal integrity purposes, as well as for power. We'll also talk about different methods and architectures to mitigate these issues. We'll use Samtec's Flyover Cable Systems, or maybe a combination of all the things that we've talked about prior. The nice thing is that you have options. If you're not ready to do a full system integration or full system switch, we may combine some of these things as we build our solutions, as we look at the traditional air cooling, the localized cooling, or the full immersion cooling. As we look at traditional airflow options, we look at the history of how we've used it in the past. The amount of equipment per square feet versus the amount of cooling needed is shown in this graph. This is from a white paper from Schneider Electric on showing how the kilowatts per rack, as they go up, the cooling is such a huge part of the necessity to keep this system going. This is only going to get worse. As we look at the future panel interfaces for system designs, we look back at the QSFP modules. If we look at the QSFP 28, these were designed for 3.5 to 5 watts of power per module. Once we add the double density or the QSFP DD, these powers went up to 12 to 20 watts per module. And now as we're talking about QSFP DD 800, we're going to be pushing 25 watts per module. Samtec worked with fellow partners to develop this white paper attached here. We're talking about the ways to cool the 25 watt thermal system using the QSFP DD system. So from air cooling, we may go to the localized cooling. And this could be a direct to chip, a fluid to chip, a water to chip, or a spot cooling, where we take small radiators or small features that we actually take just inside the system and place on top of the modules or connectors or interfaces that are needed. This will require additional plumbing coming into the box, going through your system and to that localized spot. So now let's take a look at full immersion cooling. These are different methods of creating this system, from an open bath to a closed system. You can do very high density single rack systems from 20 kilowatts to 200 kilowatts per rack. There's no additional cooling fans needed, and typically it's a much lower pressure to circulate the coolant fluid. If you would like to take a look at a full system, we worked with Submer, who creates these solutions for the backplane systems. And if you follow this link, you'll see a whole network backplane system and how the architecture was created using Samtec products. You can also go to samtec.com/testing/immersion cooling to find the products that we've tested in these situations in this coolant. So data centers are one of the larger users of immersion cooling, but it's showing up in other industries as well. So you can go to this website and find the different products that we've tested. The immersion cooling test that Samtec does includes both mating, unmating durability, insulation resistance and dielectric withstanding voltage, current carrying capacity, low-level circuit resistance, thermal shock and thermal age, as well as signal integrity testing. If you notice the series on the right side, each of these are separated by their use case. So the top green box are optical products. The next purple box are backplane products. The red box is high-speed board-to-board products. And the yellow box are power and lower speed signal connectors. We're here in the lab at Samtec where we're doing our immersion cooling test. Here, the connectors are below the liquid level and we have that controlled, and then the power coming in is coming in through the top. We cycle the current through the test and evaluate the temperature change as it goes. Samtec produces products in each of these areas. Each of them are tested in a little different way if we're looking for the high signal integrity, the high speed, or if we're looking for the high power to power your system. So let's take a look at some of the signal integrity effects due to immersion cooling. This will be critical for you to understand because most connectors are designed with an air dielectric inside the connectors in the mating interface. Well, now if we put this in an immersion cooling tank, we've changed the dielectric constant, which now can affect the signal integrity. Shown on this slide are our test tanks, where we fully immerse the connectors, but we leave the test ports out. And what you'll see is on the impedance graph, the cable, the test cable, the SMA, the trace into the board, and then the connector, the red line being for air, and the blue line being the immersion cooling liquid. As we dig into the signal integrity plots, we'll look at insertion loss, return loss, near end and far end crosstalk, and the effects that are played by the immersion cooling. This series that we're looking at is the ERM8 and ERF8, or the edge rate series. Again, the air is in red and the coolant is in blue. You see a slight shift on the graphs based on the coolant to the left. What this looks like is that the coolant does have an effect, but for this speed and this connector, it's less than 7% overall. So the resonant points do shift at the lower frequency, and the propagation delay increases at the lower impedance. These are shown by the red and blue graphs. What's causing this is what was mentioned earlier about changing the air cavities inside the connectors. So the same connector that we were testing in the previous slides are shown on these images on the right. The blue areas are the air cavities that were replaced from the air dielectric of 1 to the immersion cooling liquid dielectric of 2.1. Once we correlate these measurements to the simulations, now we can correlate these and simulate these for future designs. Being able to correlate the test data versus the real life data allows us to simulate these going forward so that we don't have to design the system, then fully immerse the system and test it. We can simulate that ahead of time. If we look at other products and how it affects the power integrity, that's where you see some major benefits from immersion cooling. The series shown now on the screen is Samtec's C-Ray. And if you look at the current carrying capacity from our test reports on the website, you'll see that if we fully populate this or fully power every single pin in this connector, we average about 0.5 amps per contact over the 500 contacts in this system. Now in immersion cooling, where we fully have the system, the connector mated and in the liquid, we go from that 0.5 amps per pin to 2.5 amps per pin. This takes our aggregate amps from 250 to 1250 for the full connector. Another series to look at is our ET60, or our power connectors. These go a step farther, where in air, if we fully populate 6 power blades, we get 52.3 amps per pin. If we fully submerge this connector, we go up to 161 amps per pin. So going from 314 amps aggregate to 970 amps aggregate over those 6 pins. If we move away from the immersion cooling, we go into an architecture change. This may be localized cooling, using a Samtec Flyover Cable solution, a low profile design, or a modular design to readjust your system and the architecture. As we talk about some architecture changes, let's look at this localized cooling case study. This is the same ET60 series that we heard about early in immersion cooling. This is where Samtec and the simulation team looked at different architectures of applying localized cooling. If we look at the same ET60 connector, fully powered, trying to push 15 amps per contact over the entire assembly. We created 3 different scenarios with different boundary conditions to look at where does the heat go and how can we apply localized cooling to just isolate that heat and remove it without incorporating the entire system into a cooling system. The 3 different options that we chose were applying a cold plate, a heat sink, and then a heat sink with a heat pipe attached to try to keep our maximum temperature down to fit the customer's application. What we ended up doing after running these evaluations was go to a localized cooling system where we took the heat pipe into the heat fins and circulated coolant through the system just over top of the connector itself. This change allowed us to keep the maximum temperature below 60 degrees and kept the temperature rise under 30 degrees, which was the customer's requirement. By simulating these effects and modifying and optimizing where these localized cooling spots are, Samtec was able to produce an efficient system that met all the customer's demands. Now, if we look at a larger scale optimization, this is where the entire system is in question and not just sending in localized heat pipes and localized cooling. Now we're modifying the entire architecture, the layout of the box. What you see on the left side is a conventional network switch where both the ASIC and the front panel connectors are very close together because of the signal loss through the printed circuit board. What we're talking about with Samtec cable flyover solution and the modular architecture is spreading these pieces out. And so the image on the right side is pushing the ASIC farther away from the front panel, closer to the fans, and farther apart from the front panel heat. What this looks like in a thermal simulation is the traditional architecture on the left. The heat is all towards the front, and the air flowing from the front to back, or the top to bottom in this image, it carries that heat farther into the system. By separating these items and separating these features, we're able to move the hot spots both from the front into the middle and give the air more efficient path to cool the ASIC and the modules. The way we're able to do this in the Samtec flyover cable option and through this demo that we have is because the cable used is 3 times less lossy than the printed circuit board equivalent. So we're able to move the high-speed signals 3 times farther away from each other so that we can move the heat sources back and forth. So as we transition from immersion cooling, now let's talk about changes to the architecture of an existing system. You can position yourself for success by looking at localized cooling, using Samtec flyover cable solutions, a low profile design, or a modular design. The image on the screen is this chassis that we have here, where the fresh air comes in through the front face and passes over the Samtec FQSFP DD. The air flows past the pin fin heatsink, cooling the transceivers. This then transitions into the high-speed, high data rate cable that takes the signal from the front panel to the ASIC. The signal goes through the Accelerate connector family near the ASIC to take the high-speed signals directly into the chip. By separating these from the front to the back, we've allowed more airflow and more efficiencies in the design to cool the product. In this case study, the simulation engineers took multiple options and improvements through the design. Changing the pin fin heatsink on the FQSFP DD, to changing the heat pipes over the ASIC, to changing the positioning of all these things, utilizing the Samtec Flyover cable, we were able to, by margin, the red line on the graphs are the limits, where before improvements were made, we were over the limits in some cases at the ASIC junction. But through these efficiencies, we not only gained improvements on the ASIC junction, but also on the transceiver, so that if we had to go to the FQSFP DD800, we have room for the temperature to change. This is possible through using Samtec's high-speed cable. Were mentioned before, this is 3 times the performance of traditional printed circuit board materials. By having a co-extruded twin-ax cable, we can control the skew and the impedance and the signal integrity through the entire channel. This graph shows the improvements in efficiencies as we go beyond 56 gig PAM4 to 112 gig PAM4 and beyond. Samtec provides tools to help evaluate and develop your system before you go through the whole architecture change. These are through our kits and evaluation boards found at samtec.com/kits. I'm here in the lab at Samtec, where we take the simulations shown in the case studies and we correlate that to live data. And so in this wind tunnel, we were able to mimic the customer's application through the airflow, through baffles that simulate the system architecture, and then through the readout that checks the thermocouples, the temperature, as well as the signal integrity as we go. We take the same FQSFP DD family and we're able to modify different heat sinks to simulate the best performance and the highest thermal efficiencies from the airflow. These systems will be shipped to you to run your signals and your system before fully designing the architecture. In conclusion, each of these cooling methods has its pros and cons, from air cooling to localized cooling to immersion cooling. Spreading out the heat sources or combining localized cooling methods may buy you time before you have to jump into full immersion cooling. Accurate correlation with your simulations can help with the iterations of your designs and make them more efficient so that you don't have to iterate them time and time again. The correct component design and support can ensure signal integrity and thermal management are maintained. Samtec is ready to help you with these designs and help you with your new architecture. We take both our product families and the innovation in material science and combine them to create new solutions to help improve thermal management in your system. If you have questions about thermal management with your connector designs, please reach out. Thank you for your time. My name is John Riley, Senior Technical Marketing Engineer here at Samtec.